seems like we should probably talk about limits today, I would imagine, because limits. And there's really kind of a lot to say about limits because there are so many different ways we try to kind of evaluate them. So I'm going to start at what I feel like is the logical place, just kind of seeing what a limit looks like. So let's look at this function. Let's write some important information. Co-16A, today is October 5th. Yeah. Cool. So let's graph this piecewise function. F of x equal to, what do I got here? I should put these notes closer to where I can see them. What have I got? So the pieces are x cubed plus 1 when x is less than 0, x plus 1 when x is bigger than or equal to 0 and less than or equal to 2. And finally, x squared plus 1 when x is strictly greater than 2. And I should turn off these. I feel like we did the light better last time. Let me see if I can make it look a little bit less terrible. Think of this. No, that's the wrong way. Do this. Yeah, it's so dark. No, it doesn't get bright. Yeah, I guess that's better though, right? Yeah, okay. It is what it is. Look, I got. I don't love that this is casting a shadow like that, but I don't think I can. No, I don't think. Nope, it's not going to be better if I do that. Okay, so sorry. So let's graph this thing. So when we're graphing a piecewise function, we're just kind of looking at each domain and graphing the function on that domain. So the function x cubed plus 1 looks like your usual cubic function, but gets up 1. So, and that's going to be when x is less than 0. So over here on the left side, I'm graphing the cubic function. And it's going to look kind of like this. It's not the function I'm the best at graphing, but it kind of looks like that. There's your cubic function when x is less than 0. All right, we're over here on the left side. I kind of like to do this. And then we're going to graph the straight line y equals x plus 1 when x is from 0 to 2. So if you plugged in 0, 0 plus 1 is 1. This should have been an open circle here for a second. But now we're closing it up because we're getting that same point at 0, 1. And then straight line from the point 0, 1, if we plug in 2, 2 plus 1 is 3. So we're just going over to the point 2, 3. And that's a straight line from there to there. And then finally, we're going to get the graph of y equal to x squared plus 1 when x is larger than 2. So that's an upward opening parabola, shifted up 1. What I'm really going to do, though, I know the parabola looks like, I'm just going to draw it in the air. It looks like this, right? There's my parabola looking like that. And I know that I'm going to get kind of some of the right side of it. So I'm just going to plug in x equal to 2, even though I can't really. 2 squared plus 1 is 5. So up to 5. And if I could plug in 2, I would get 5, but I can't. So I'm going to draw an open circle there instead. And then the graph would look like parabola up like that. And then it actually starts right there like that. So there's my piecewise function. One second. I should say my clearly discontinuous piecewise function. Right? Not. I know we haven't talked about continuity yet, but it's good to have a kind of a layperson's idea of what continuity looks like. It looks like you can draw the graph without lifting your pencil off the paper. Question, Nikki?
Yeah.
Yeah.
How did you know, how did you get 5?
How did I get 5? Excellent question. So even though it doesn't say that x is equal to 2 here, x is really, really, really close to 2. Like you could plug in, for example, 2.000000001. And 2 point lots of zeros 1 squared is really, really close to 4. It's like 4 point even more zeros 1. And 4 plus 1 is really, well, 4 lots of zeros 1 is really close, plus 1 is really close to 5. What I'm actually doing, I'm not plugging in 2.00004. I'm plugging in 2. I'm just saying if I let x equal 2, the y value there would be 2 squared plus 1, which is 5. And so what I'm really thinking of, and this is actually really what I'm describing is the idea of the limit. What I'm really saying to myself in my head is, oh, as x gets closer and closer and closer to 2 from the right-hand side, from the bigger than 2 side, the function is getting closer and closer to 5. In fact, let's write that down. using a limit notation. We would say that the limit as x approaches 2 from the right-hand side, from the bigger than 2 side of our function. So there's a couple ways you can do this. I know it's 5. We know it's 5. But if you were actually trying to show the work, like if someone said find the limit of x approaches 2 from the right and they wanted you to show some more work, it would be good to show this additional step. I know that when x is larger than 2, that my piecewise function is this piece right here when x is larger than 2. So I'm going to write that as the limit as x approaches 2 from the right of the piece that actually matters when x is bigger than 2. And here's something, here's probably the first rule you should know about limits. The first rule of thumb, like it's not like a hard and fast rule, is if you can substitute in your value for x and get a real number out, that's probably most of the time going to be the limit. So if you actually just substitute in 2, not 2.01, not a number that's a little bit bigger than 2, actually 2, you're going to get 2 squared plus 1, which is 5. Here's what this means. This means what we've already said a couple times. As x gets closer and closer to 2 from the right, the function gets closer and closer to the value of 5. It does not necessarily mean that the function ever equals 5 when x is equal to 2. In fact, it doesn't. Limits are all about closeness. What happens is x gets really, really close to this value to the y value of the function. I said that kind of badly. What happens is x gets really, really close to a number. I'm saying it badly. What happens to the function as x gets really, really close to a number? That's what we're asking about when we're asking about a limit. What is the behavior of the function as x does whatever it's doing? And again, we don't care what's happening at 2, because if you look at this function here, f of 2, if I plug in 2 to the actual function, well, to plug in 2 to the actual function, I have to use the middle piece here, because that's where x is, the function is defined when x is equal to 2. So f of 2 is going to be 2 plus 1, which is 3. We can also look at the limit as x approaches 2 from the left. If I look at the limit as x approaches 2 from the left side of 2 of f of x. So now we have to be a little bit more careful. I say that because you could say, well, James, there's lots of left sides of 2. This piece of the function is left of 2. This piece of the function is also left of 2. How do you know which one to pick? Well, we're going to pick the one where x is getting close to 2 from the left. So that would definitely be this middle piece where x is less than or equal to 2. So if I want to find the limit as x approaches 2 from the left of f of x, it's going to be the limit as x approaches 2 from the left of x plus 1. And then again, I can just substitute in, or we usually say we plug in whatever x is approaching for every value of x. I'm going to get 2 plus 1, which is 3. Okay, so now for the important, well, it's all important, like the bigger deal. No, the limit as x approaches 2 overall doesn't exist. If the left-hand limit and the right-hand limit don't go towards the same y value, the limit doesn't exist. For the limit to exist, both sides have to be getting closer and closer to the same number. So we would say that the limit as x approaches 2 of f of x does not exist, which you can totally abbreviate as dne. Questions so far? Okay. Yeah. So just some conventions, some language that I'm going to expand upon later, but I'll just point out, I know at the beginning, and I didn't actually, I was going to keep writing this here. Here's where x is between 0 and 2. And over here is where x is bigger than 2. Yeah, I meant to fill it earlier. What I wanted to say is when I do this graph, I said that it was, in my opinion, obviously discontinuous because there's a break. But what I really should have said is this graph is actually continuous almost everywhere. In fact, there's only one value of x where this graph is not continuous, and it's when x is equal to 2. So I should just point out that people use the word discontinuity kind of, I don't know, flagrantly, right? Even though this graph is continuous almost everywhere, we would still describe it as a graph that is discontinuous because there is one point of discontinuity or more. So that kind of supersedes anything else, just so you're aware. So when someone talks about something being discontinuous, they usually just mean there's like one or two places or maybe a few places where it is not continuous. But most graphs are continuous, or most functions are continuous on most of their domain, typically. And we'll see that as we go along. Yeah.
So would you need to graph a piecewise function to like find the limit?
No, you would not. You could definitely have done this without graphing it at all. You could have said, okay, if I want to talk about the limit as x approaches 2, I could have said, well, the limit as x approaches 2 from the right, I'm just going to use the piece of the function where x is bigger than 2. If I want the limit as x approaches 2 from the left, I'm just going to use the piece of the function where x is just left of 2. And then I can see that those limits are different values, so the overall limit does not exist. And you're 100% correct. You would not need to graph it at all. So let's see here. What do I want to do next here? In that same sort of vein, what about the limit as x approaches 0 without the graph? I know you have the piecewise function written down still. So what if I want to find the limit as x approaches 0 from the left? Which piece of the function should I be using? The x cubed plus 1 piece, or the x plus 1 piece, or the x squared plus 1 piece? Which one? Sorry, I think that would be if it was on the right side of 0. Yeah, so when we approach 0 from the left, we have this little minus superscript here to say that we are left. We're really like on the left side of 0, which is negative in this particular case, but in general, just left of. So we'd be using the, yeah. But just like before, if we can, we should just plug in 0 for x. So I'm going to get 0 cubed plus 1, which is just 0 plus 1, which is 1. I want to stress here, because I've seen too many people do the wrong thing too many times. You're not plugging in a number that is smaller than 0. You were actually plugging in 0. Okay. And then from the other side, the limit as x approaches 0 from the right of f of x. Then we're going to use the piece where x is just bigger than 0, or bigger than or equal to 0, however it's defined. And I think that piece was the x plus 1 piece, I think. Yeah, right? When x is bigger than or equal to 0, the function's equal to x plus 1. So if x is approaching 0 from the right, we're using the x plus 1 piece. So then that's going to equal 0 plus 1, which is 1. And then that means that the overall two-sided limit does exist. We can say that the limit as x approaches 0 of f of x is equal to 1. Never. All right, papers everywhere. Why are you all? Sorry. Yeah. Cool. Here's what oh yeah, question.
It's kind of like similarly to the piecewise function. If it was like equal or doesn't equal to 0, how would you just not plug it into that equation?
So
like x squared plus 1 and then comma x doesn't equal 0.
Like if it like, oh, so let me, I'm not exactly sure. Let me give an example that I think is what you mean. So if we had some other piecewise function, like say g of x was equal to x squared minus 9 over x minus 3 when x doesn't equal 3.
Right.
And say 4 when x does equal 3.
Right.
So here it's actually kind of almost easier in a sense, because if you want to look at the one-sided limits from either side of 3, well, whether x is bigger than 3 or x is smaller than 3, the function is equal to this. So I could do them separately, but it'd be kind of a waste of time. I can say that the limit as x approaches 3 from the left of x squared minus 9 over x minus 3, and also the limit as x approaches 3 from the right of x squared minus 9 over x minus 3. But since whatever I end up doing, I'm essentially going to do the same work, right? Whatever factoring, canceling, plugging in, whether it's 3 from the left or 3 from the right, I'm still going to plug in 3 when I try to evaluate the limit. I don't need to do them separately. I can just kind of be like, oh yeah, I'm just going to throw that into one good limit here like this. You typically, if you're trying to evaluate a limit, you really only need to look at the two different sides at a particular point if it's a piecewise function. Most other functions, the left and the right-hand side will be the same. One exception to that, well, it's actually not really an exception, but we'll see one exception is the absolute value function, but really the absolute value function is just a piecewise function, so it's not really an exception to what I just said. Cool. So here, if you try to plug in 3, you can't, right? If you plug in 3, you get 0 over 0. So what do we do when we get 0 over 0? You do more work. 0 over 0 means you have to try something else. Usually that means, in the words of my colleagues, do some algebra. So here we can factor. X squared minus 9 factors as x minus 3 times x plus 3. And then we can cancel the x minus 3s, or I should say x minus 3 divided by x minus 3 is 1. And then we've got the limit as x approaches 3 of x plus 3. And then we can plug in 3, since we no longer have division by 0 as a potential problem here, and our limit is 6. And that would have been true whether I did it from the left or from the right. So I can just kind of do both sides at once here without having to worry about that. Is that what you meant, Nikki? Yeah. So, yeah, let's look at a few more examples here. So let's evaluate some limits. Let's say I want to find the limit as x approaches 2 of x squared plus 3x plus 4 over x plus 2. And before you do anything else, right, you might, so the problem with limits really in this class is you're going to get very used to seeing 0 over 0. It's going to happen a lot. And so you might start making just the blanket assumption, oh, it's 0 over 0, I should factor or get a common denominator or do something else. But before you do that, just at least check to make sure it's actually not 0 over 0. Because if we plug in 2 here, I'm going to get 2 squared plus 3 times 2 plus 4 over 2 plus 2, which is going to be 4 plus 6 plus 4 over 4, which is 14 over 4, or 7/2. Or 3.5 if you like a decimal, but I don't like a decimal really, so I'm leaving the 7/2. That's it. That's our answer. We're done. That is the limit as x approaches 2. No other thing to do, really. Or we could even have something like the limit as x approaches 1 of the cube root of 2x plus 6 plus e to the x minus 1 plus 3. In fact, you also do this one. Plug it in, see what you get. The answer is one of my favorite numbers. Those of you on the Zoom, I should just remind you, you're all welcome to ask questions if you got them. And if you write something in the chat and I don't see it, I imagine someone in the class would see it on the screen. So if I'm ignoring you, speak up, or someone else will speak up for you. All right, let's see what we get here. So again, just doing the usual thing, I'm going to plug in 1 for every x. So I'm going to the cube root of 2 times 1 plus 6 plus e to the 1 minus 1 plus 3. 2 plus 6 is 8. Cube root of 8 is 2. And e to the 0, right? Anything to the 0 is 1. Plus 3, which is 6, which is a great number. Why is it great? Well, come see me in office hours. I'll tell you all about why 6 and 28 are both really interesting numbers for reasons I will leave to be discovered. It's not important. It's just something interesting. It's not important at all, though. Let's look at another one. X squared plus 4x minus 21. Sorry, I should have said the limit is x approaches 3 of x squared plus 4x minus 21 divided by x minus 3. And here now we're going to encounter the thing you're often going to encounter, which is, again, we've got a 0 over 0. If you plug in 3, 9 plus 12 is 21, minus 21 is 0, 3 minus 3 is 0. I don't think you actually need to write that out, but you should at least check in your head. And you can certainly write it out if you want to, but certainly check at least to make sure you got 0, 0, 0 over 0 before you start doing something like this. I'm going to factor. I should also mention at this stage, L'Hopital's rule is not on the table, right? If you've heard of L'Hopital's rule, great. You can't use it yet. So if you haven't heard of it, also great because you can't use it yet. So don't worry about L'Hopital's rule if you haven't heard of it. Don't use it if you have. Here's what I would point out. And I know I said this, I think I said this before, but I'm saying it again. If I plug in 3 here and I get 0 on top, that means x minus 3 had to have been a factor. So I know right off the bat, x minus 3 is one of my factors. And then I need an x here because so x times x is x squared. And I need a plus 7. So the negative 3 times positive 7 is negative 21. It's a really easy way to kind of start off the factoring process. And then just like before, things divide to 1. X minus 3 divided by x minus 3 is equal to 1. So I've got the limit as x approaches 3 of x plus 7. And then we substitute in 3 and we get 3 plus 7, which is 10. I should really, really emphasize here. This function, x squared plus 4x minus 21 over x minus 3, and this function, x plus 7, are the same everywhere except for one place, when x is equal to 3. This function is totally undefined when you plug in 3. This function is not. So what we can say is that this is equal to this as long as x isn't 3. So they're the same everywhere except at 3, which means that as x gets really, really close to 3, since they're the same everywhere except at 3, they both get close to the same value, right? Here you can just see, oh yeah, 3 plus 7 is 10. Whereas over here, and then I think I tried to do this last time, I kind of blew it, I'm not gonna lie. If you plug in something really, 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 really close to 3, like say x equal to 3.001, well, 3.001 minus 3 times 3.001 plus 7 over 3.001 minus 3, this divided by that is 1. And so you're left with 3.001 plus 7, which is 10.001. So we can see that, oh yeah, as we're getting x values that are closer and closer and closer and closer to 3, the function values are getting closer and closer and closer to 10. Now, we don't do it this way because it's a pain, but that's the idea. But that's why this works, is that you say, oh, well, what's happening at 3 doesn't matter, so I can cancel the x minus 3s and not have any problems. And then you can just substitute in 3 for the remaining x, which is nice. Cool. Questions before we do more like this? More algebra things. Okay, so here's what I would say. Yeah. In fact, why don't you all try this one? We'll do this one together. The limit as x approaches 1 of 4x squared plus 5x minus 9 over 6x squared plus 7x minus 15. So if we plug in 1, we get 4 plus 5 minus 9, which is 0. 6 plus 7 minus 13, which is also 0. So we're going to do some algebra. And the reason I say do algebra is because we're going to talk about a couple other algebraic things we do other than factoring. All right, so you all know something. You know that I plugged in 1 and I got 0 on the top and the bottom. So that means both on the top and the bottom, what should one of the factors be? If I plug in 1 and got 0, x minus 1 had to have been a factor. All right, I want you to use that to figure out what the other factor is on the top and on the bottom. In fact, I'll give you the top one.
There's a little spider on the floor.
Kill the fire. No, I'm just kidding. It's a daddy long legs. It's fine. You're welcome to move seats. Oh, or we can just do that. That's totally fine. So I'll point out here that I got a 4x plus 9 here because I knew that x times 4x had to give me 4x squared, and minus 1 times 9 had to give me negative 9. In the same sort of way, you all should find what's going to go here. X times something has to give you 6x squared, and minus 1 times something has to give you minus 13. Give you like else. So here's what you should be getting. I need a 6x here, so that x times 6x is equal to 6x squared. I need a plus 13 here, so that minus 1 times 13 equals negative 13. And the thing is, we know, because we plugged in 1 and we got 0 on the top and on the bottom, that this works. X minus 1 has to be a factor. This other factor has to be exactly this to make it work. We can check. Right? If you actually multiply this out, x times 4x is 4x squared. Negative 1 times 4x is negative 4x. 9 times x is 9x. And 9x minus 4x is 5x. Minus 1 times 9 is minus 9. Same on the bottom. The parts we've already done work. X times 6x is 6x squared. Negative 1 times 13 is negative 13. And then the middle parts give me a negative 6x plus 13x, which is exactly 7x. You don't need to check this though. If you know that you plugged in something and it made it 0, you know that x minus that number is a factor, and then the other factor is usually not too terrible to find. So then x minus 1 divided by x minus 1 is 1. So we're left with the limit as x approaches 1 of 4x plus 9 over 6x plus 13. And then we just sub in a 1. So we get 4 plus 9 over 6 plus 13, which is 13 over 19. And that is the limit. All right. Sure, one more of these style, and then we'll change it up. Yeah, this one's fun. And the limit as x approaches 2. Let's do it negative 2. Limit as x approaches negative 2 of x squared minus 5x minus 14 over x cubed plus 8. And let's check, because I just changed the problem, so let's make sure that it's not something crazy. If we plug in negative 2, we're going to get negative 2 squared minus 5 times negative 2, which is plus 10, minus 14, over negative 2 cubed, which is negative 8, plus 8, which is, in fact, 0 over 0. Okay. So we have some algebra to do. We have some factoring to do. The top shouldn't be too terrible. If x is approaching negative, if we plugged in negative 2 and got 0, all right, I want everybody to write down what the factor we know for sure is going to be. You can write it as x minus something, or if you want to simplify it, you can write it as x plus something. All right. So on top, x minus minus 2 should be our first factor, or I would write it as x plus 2. Also on bottom, right? I mean, we plugged in negative 2 and got 0 for both the top and the bottom. So x plus 2 should be a factor. On top is not too terrible to deal with. I should get an x, and is it a plus 7 or a minus 7? Yeah, minus 7. On the bottom, it's a little bit more work. So there's a way of factoring a difference of cubes that you may or may not be aware of, but you will be aware of it in just a moment. So if you have, or a difference or a sum of cubes, excuse me. If you have a cubed plus b cubed, it factors as a plus b times a squared minus ab plus b squared. And in a similar way, in fact, I'm just going to change the sign right here. If you have a cubed minus b cubed, you get a minus b times a squared plus ab plus b squared. There is an acronym for this that I think is somewhat clever. The acronym is SOAP. And the letters stand for the signs. So the first sign here is the same as what you started with. So if it's a cubed plus b cubed, it's going to be a plus b. And then the next sign is the opposite of what you started with. So if it's a plus here, it's a minus here. If it's a minus here, it's a plus there. And finally, the last one is always positive. You do have to remember the pattern, right? That it's a either plus or minus b, and then a squared, ab, b squared. But the SOAP will tell you what the signs are. It's kind of nice. It works. So that means here, since we had x cubed plus 2 cubed, our x is like our a, our 2 is like our b. So we're going to get x plus 2 times x squared minus 2x plus 2 squared. And that's how that factors. If you want to check it on your own, you can FOIL it back out. It's a little bit of a pain, but right, if you multiply everything through, you should end up getting x cubed minus 8. The middle term should cancel out. And they do. And then we do the usual thing. X plus 2 divided by x plus 2 is 1. We're left with the limit as x approaches -2 of x minus 7 over x squared minus 2x plus 4. And that's going to be -2 minus 7 over -2 squared, which is positive 4. Minus 2 times -2 is plus 4 plus 4, which is -9 over 12, which reduces to -3 over 4. Couple things I should mention as we do this. Every step of the way, well, maybe not every step, but almost every step of the way, you should be writing the limit as x approaches -2 or whatever x is approaching, because every step of the way you're asking the question, what is this function getting closer and closer to as x is approaching -2? And then at the moment when we plug in -2, we no longer write the limit, because now we're answering the question. Oh, the limit is this value here, which we're then just simplifying and simplifying. So once you plug in the x value, you no longer should write the limit. But up until that point, you should always be writing the limit. Questions before we use some different algebraic things? Loads of time. Cool. Let's see if I remember some names. Anthony, Kelsey, Erica, Nikki, Peyton, Carrie, Bere, Maya, Natalie. Cool. And what's your name? Sorry, over here in the front. What's your name? Lasasena. All right, so I'll work on that one. Sorry. And you? Solara. And you? Ruben. Cool. How do you spell your name? A-S-U-S. Okay. I was hearing an L for something. Asusena. Yeah. Okay, cool. I think I will probably be able to get that without too much effort. Seeing the spelling always helps me because I'm like, okay, I know what I'm actually supposed to be trying to say, kind of. All right. Let's do some different algebraic things, like the limit as x approaches 2 of 3 minus the square root of x plus 7 over x squared minus 4. Once again, 0 over 0. You plug in 2, you get 3 minus 3 on top, 4 minus 4 on the bottom. So there's actually a couple things going on here. When you see square roots, the only way we really can deal with them is by multiplying the top and bottom by the conjugate of that thing that has the square root. So I'm going to multiply the top and bottom of this expression by 3 plus the square root of x plus 7 over 3 plus the square root of x plus 7. And now I can't remember because I teach a lot of classes. Did we talk about conjugates last time in class? Okay, cool. So we know that when you multiply something by its conjugate, you don't get the middle terms, right? You just get the first term squared minus the second term squared. So when we multiply this out, here's what's going to happen. Right, the limit as x approaches 2. And on top, we're going to get 3 times 3. The middle terms we cancel. I'm not going to write them, but I'm just going to show you. You would get 3 times the positive square root of x plus 7, and then you would get 3 times the negative square root of x plus 7. And if you add those together, they add to 0. So we're not going to write them. And then we're going to get minus the second thing squared. Square root of x plus 7 times square root of x plus 7. And I think you can skip the step of writing them out like this, but I'm writing them to kind of just show everyone what's happening. And on the bottom, we should really also factor this here because we know that the x minus 2 is kind of what's causing a problem. We know that when we plug in 2, we get 0. That means we need the x minus 2 part to cancel out. And to be able to cancel it out, we really need to factor it if it's not already showing up easily. So I'm going to factor that as x minus 2 times x plus 2. And then I also have this other 3 plus the square root of x plus 7 down here. I don't want to multiply anything out in the bottom. You could, but you really shouldn't. What we want to do is we want to simplify the top here. So let's see, we've got the limit as x approaches 2. 3 squared is 9. Minus all of x plus 7 is really minus x minus 7, because the minus sign would distribute to the minus x plus 7. Over, same thing, x minus 2 times x plus 2 times 3 plus the square root of x plus 7. Let's simplify the top even more. In fact, I probably could have done that in one step. Oh, well, sometimes we don't do it in one step. Oh, yeah, this is a good thing. So let's see. We got the limit as x approaches 2. So 9 minus 7 is 2 minus x over x minus 2 times x plus 2 times the same deal. Yeesh. Now I have problems. 2 minus x and x minus 2 aren't the same. They don't cancel out. They don't divide to 1. There's a couple ways you can go about dealing with this. One way is to know that when you subtract things in the opposite order, they are opposite signs. For example, what's 7 minus 5? What's 5 minus 7? What do you get when you divide those by each other? What's 2 divided by negative 2? Right, negative 1. So whenever you have things subtracted in the opposite order divided by each other, you're going to get negative 1. So the shortcut way of doing this is just saying, oh, these divide out and leave me with a negative 1. So you can, I'm gonna add an extra step here to show you another way of doing it. But you could just say, go straight to saying this is equal to the limit as x approaches 2 of negative 1 over x plus 2 times 3 plus the square root of x plus 7. But if you don't like that, an additional step you can take is to factor out a negative 1. I would do it in the numerator here. So if I factor out a negative 1, I'm left with a negative 2 plus x, or I would write that as an x minus 2. And then it's easier to see that the x minus 2 divided by the x minus 2 is just 1. Then x minus 2 divided by x minus 2 is just 1. And then you're still left with the limit as x approaches 2 of negative 1 over x plus 2 times 3 plus the square root of x plus 7. Finally, we can plug in x equal to 2. You get negative 1 divided by 2 plus 2 times 3 plus the square root of 9 is 3, which we should simplify as negative 1 over 20. Okay. Okay. Let's look at another example. I'm tired of the x approaching 2 examples, but let's do something slightly different here. Let's say we have a limit of x approaches 3 of 6 over x minus 2 over x minus 3. Which, not surprisingly, again, is a 0 over 0 type of limit. 6 divided by 3 is 2, 2 minus 3 is 0, 3 minus 3 is 0. So now what do we do? We have fractions and fractions. Oh, and there's a couple different ways people like to do this. But the way I would say that we should do this is we need to be able to subtract these, so we need a common denominator. So let's write that as a 2 over 1, and then multiply this 2 over 1 by x over x. So that you end up getting, I'll show you a different way of doing this one too, because there's a kind of a slicker way of doing it that I think you might like to be aware of. It's going to be the limit as x approaches 3 of 6 over x minus 2x over x all over x minus 3. Then we're going to put those together. We get the limit as x approaches 3 of 6 minus 2x all over x, all divided by x minus 3, which I really don't love fractions and fractions. This is not my favorite. So let's do two things at once. Instead of dividing by x minus 3, we can multiply by what? Sorry, you're all whispering. I can't. My hearing is not excellent, in case you didn't know. What was the thing you were saying? Not quite x plus 3. So if we let me make it a little bit easier to maybe see. If we want to, instead of dividing by x minus 3, we'd like to multiply by the not the conjugate here, although that's not that, which would the conjugate would be x plus 3. We want the reciprocals we want. So when we're dividing by a fraction, the people say like copy dot flip, or there's there's lots of things people say, but we really like actually let me show the steps because I think it's worth seeing here. What we're actually doing here is we're saying I'm going to multiply the top and bottom of this huge fraction by the reciprocal of that bottom part. So I'm going to multiply the top and bottom by 1 over x minus 3. But what's x minus 3 over 1 times 1 over x minus 3? 1, right? Right? You get x minus 3 over x minus 3, and that's just 1. So then we end up getting, I was going to do something here, but screw it. 6 minus 2x over x times 1 over x minus 3. And that just makes it easier to write the expression, right? Fractions and fractions are nobody's friend, in my opinion. Okay, so then we should do a little bit more simplifying. I know that the 3 is the problem, so I know that so what do I need to factor, or what do words? I want what to show up if 3 is a problem. Well, I've got an x, right? The x minus, I should really say the x minus 3 is the problem, right? So you plug in 3, you get 0. So I need the x minus 3 to show up if 3 is what x is approaching. I need an x minus 3 here, which I've got. I would love to have an x minus 3 up there as well. So what would be the best thing to factor out from the top to make my life as easy as possible? Positive or negative 2? Positive 2 will work. So factor out a positive 2. Let's see, I get 2 times 3 minus x over x times x minus 3. And then we know that 3 minus x divided by x minus 3 is going to be a negative 1. And then we can plug in the 3 and get negative 2/3. I will mention, we could have also factored out a negative 2 instead. We could have gone from here and said, we're going to do the limit as x approaches 3. If we factor negative 2 from the top, we're left with a negative 3 plus x over x times x minus 3. But negative 3 plus x is the same as x minus 3. It's just written in the opposite order. X minus 3 divided by x minus 3 is just 1. So this would be the limit as x approaches 3 of negative 2 over x, which is negative 2/3. Either way, it gets you to the same place. It just depends on what you want, which way you want to see it. So let's sum up our algebraic methods. They're not the only method, but they're kind of the main ones. So for 0 over 0 limits, the first thing you should try is some algebra. Specifically, factoring. And really factoring is always going to come into play, right? Whether you first have to maybe multiply by a conjugate or get a common denominator, usually after you do either one of those things, you will still then have to do some factoring and eventually some canceling out. But these are kind of the main things we do when we have a 0 over 0 limit. We factor, we multiply by the conjugate, we get a common denominator, and then we try to work with it until we get the problematic factor to cancel out. I should really say divide out. Questions about what we've done so far? So those aren't the only kinds of 0/0 limits. There are other ones as well. I don't imagine, I should just double check though. I don't think anyone's talking about sine of x over x. Good. Okay. I don't think they will, but sometimes some people talk about it, so I just want to make sure. If either teacher does, let me know and we can certainly cover it, but it usually gets kind of skipped over. Well, let's look at something else, like the limit as x approaches 6 of the absolute value of x minus 6 over x minus 6. So, fun fact, the absolute value function is just a piecewise function. But it's such a popular piecewise function that we've given it its own name so that we don't have to write it piecewise every time. But here's what you should really know. In fact, actually, let me ask you all a question. Do you know what letter of the alphabet the absolute value function looks like? It's an upside down A or a V. So when you draw y equal to the absolute value of x, all we're saying is that if x is positive, you get the same positive number back. So like if x is 1, y is 1. If x is 2, y is 2. If x is 3.4, y is 3.4. But if x is negative, you get the corresponding positive value back for y. Or another way to think about the absolute value function is it's how far x is from the origin. It's the 0. It's the distance. So when we graph this, it looks like this. If x is 1, y is 1. If x is 2, y is 2, and so on and so on and so on. For any positive value of x, you get the corresponding positive value for y. But if x is negative, you still get positive values for y. So if x is negative 1, y is 1. If x is negative 2, y is 2. Okay, and here's what I would love for you all to know deep in your hearts. When you write the absolute value function, you're really writing a piecewise function. On the right side here, what's the equation of that line that goes to the point 1, 1, and 2, 2, and 3, 3, where the x and y values are the same? It's y equal to x. Oh, I didn't mean to write the y part though. Sorry. So the absolute value of x is just x if x is already positive. If x is 5, the absolute value of 5 is 5. If x is 23, the absolute value of 23 is 23. But if x is negative, like for example, if x is negative 5, what's the absolute value of negative 5? Everybody. Right. How do you turn negative 5 into positive 5? Right. You do the negative of that negative. So the absolute value of negative 5 is negative 5, which is positive 5. So the absolute value of x is equal to negative x when x is already negative, which makes sense because this line here, that line is the line y equal to negative x. This line here is the line y equal to positive x. So that's how the absolute value function is a piecewise function. And then you can put the equals to part on either piece. It doesn't matter. You can put it here or there. Nobody cares. People change it up all the time. I don't know why. There's no, I mean, it doesn't matter because whichever place you define it to be, you're still going to get 0 for y when you plug in 0 for x. All right, so back to this. That means this is really a piecewise function. And we kind of have to think about what's happening on either side of 6. So we're going to look at the limit as x approaches 6 from the right-hand side first. Why? I don't know, because I'm right-handed, because it's just the side we usually pick first. So if x is x bigger than 6 or smaller than 6 here? Bigger. So if x is bigger than 6, x minus 6 is negative or positive? Positive. And so if the stuff inside the absolute value is already positive, you don't really need to do anything. You just can drop the absolute value and say, oh, that's equal to the limit as x approaches 6 from the right of x minus 6 over x minus 6. Right? If you pick a number bigger than 6, like 7 or 8 or 9, and you plug it in, 8 minus 6 is 2. The absolute value of 2 is just 2. Bless you. So x minus 6 divided by x minus 6 is 1. And it's really important here that we're looking at doing this division before we're evaluating the limit, right? We're not plugging in 6 and then getting 0 over 0. We're saying, oh, x minus 6 over x minus 6 is 1 as x gets closer and closer and closer, but not equal to 6. Right? Again, limits, you're getting really, really close to the number, but never actually getting to the number that x is approaching. And I'm saying, okay, well, the limit of a constant is just a constant. If your function is equal to 1 all the way up until you get to 6, then the limit's just 1. Okay, now the left side. If we approach 6 from the left, well, now x is less than 6. And so x minus 6 is not positive, it's negative. And to turn a negative into a positive, you multiply it by a -1. So we're going to write the limit as x approaches 6 from the left of -1 times x minus 6 over x minus 6. I just want to point out that if you pick a value of x that's less than 6, the top part will be positive. If you plugged in 4, 4 minus 6 is -2. -2 times -1 is +2. So it's still giving us positive outputs like the absolute value has to. But then x minus 6 divided by x minus 6 is 1, but we're left with a -1 on top. So we get the limit as x approaches 6 from the left of -1, which is -1. Which means that our overall limit does not exist. The right-hand side and left-hand side are getting closer and closer to different numbers. In fact, we could totally graph this. Again, you don't need to graph it, but it's nice to see the graph. So 6 is the point of interest. And we can see that if you pick any number bigger than 6, the function is equal to 1. Everybody should pick a number bigger than 6 in their head and then plug it into the opposite value of x minus 6 over x minus 6. Did you get one? Did you get one? I got one. I plugged in 27. 27 minus 6 is 21. Absolute value of 21 is 21. 27 minus 6 is 21. 21 divided by 21 is 1. So yeah, any number larger than 6, you're getting a value of 1. If you plug in 6, it's undefined. Similarly, any value of x less than 6, like I'm picking 4, you might pick 3, someone could pick -20. 4 minus 6 is -2. Absolute value of -2 is +2. 4 minus 6 is -2. 2 divided by -2 is -1. So any value less than 6 for x is giving me a y value of wow, that looks terrible. Sorry. It's giving me a y value of -1. And so you can see here, oh yeah, the left side and the right side are not matching up as we get closer and closer to 6. So our limit as x approaches 6 does not exist. Any other limit would exist, but not as x approaches 6. Yeah.
Would this be discontinuous?
This function is definitely discontinuous. In fact, and we'll see, probably not today, that when a function has a limit that does not exist somewhere, that function is automatically discontinuous there. In fact, having the limit existing is one of the requirements for continuity. Maybe we'll end the day with talking about the definition of continuity. But there's a few more limit things to talk about. Yeah, like this kind of limit, which is, so I saw that there's like I think you guys are jumping ahead to like section 3.6 or something, which has vertical asymptotes, which are really just the result of something happening with a limit. So let's look at another type of limit. Not a 0 over 0. Specifically, what I refer to as, well, let's look at an example first. Limit as x approaches 3 from the right of 3x minus 11 over x minus 3. Okay. So I'm just going to plug it in just like I always do. Not always, but most of the time. You plug in 3 on top, 3 times 3 is 9, 9 minus 11 is -2. If you plug in 3 on the bottom, you get 3 minus 3, which is 0. Okay, so just to kind of go back for a second, I call these a not 0 over 0 limits, which is different than 0 over 0. 0 over 0, your answer can really end up being any real number. When it's not 0 over 0, your options are limited. Thanks, appreciate it. So, you really only have like 2 or 3 choices for what the answer is actually going to be, which is nice as long as you remember that that's what's going on. So here's what I want to point out. We don't actually have 0 in the denominator there. What you have is a number. That's a number really close to 0. And I want to point out, since we're approaching 3 from the right side of 3, that means that x is a tiny bit bigger than 3. And so then x minus 3 is really a number that's a little bit bigger than 3 minus 3, which is going to be really, really close to 0 and positive. So this is a number that's really close to 0 and positive. For example, 1 over 100,000. Right? I could plug in the number 3 plus 1 over 100,000, which is really, really close to 3 and a little bit bigger than 3. What happens when I do that? Well, if I actually have -2 divided by 1 over 100,000, okay, just like before, when we divide by a fraction, what do we actually end up doing? We have -2 times, what's it called again? There's like 3 words you could use. You could use the word reciprocal or inverse or flip if you like. So when you divide by a fraction, it's the same as multiplying by its reciprocal. So -2 times 100,000 is a pretty big, it's a pretty negatively big number. It's -200,000. So what this means is that as x gets really, really close to 3 from the right, this function gets very, very negative. And I can make it as negative as I want, right? If I picked a smaller number like 1 over a billion, or I should say 3 plus 1 over a billion, my result here would be like -2 billion. So I can make this as negative as I want to. So here's what I'm going to say. This limit is -infinity. Now I'm going to do a couple things here too. When I write this here, I like to write a negative, whatever's on top, divided by a 0, in this case with a positive superscript. That's just telling me that I know I have a number that's slightly bigger than 0 or slightly positive. Helps me know that I have a negative divided by a positive, and a negative divided by a positive is a negative.
So would this typically mean it does not exist?
Yes, it would also mean it does not exist. So when we say that the limit is equal to, and that's right, equal to is kind of misleading here. When we say that the limit is equal to -infinity or positive infinity, we are saying really, we're saying the limit does not exist and gets negatively large without that. So really what I would say is when you say that the limit is -infinity or positive infinity, you're just trying to be more informative about how the limit is not existing. So this means graphically, is that as x approaches 3 from the right-hand side, the function gets very, 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 very negative. Like, sure. Like that. So as x gets closer and closer and closer to 3 from the right, the function gets more and more and more and more and more negative. So when you have a not 0 over 0 type of limit, what that means graphically is that you have a vertical asymptote. Let's look at the other side. Let's look at the limit as x approaches 3 from the left of 3x minus 11 over x minus 3. The top isn't going to change. I'm still plugging in 3 to the top. I'm still getting 9 minus 11, which is -2. However, the bottom is going to change just a tiny bit. Because when you plug in a number that's slightly smaller than 3, you're getting a very, very slightly negative number. Which I'm going to write as 0 superscript minus sign. Here's what I know. I know that not zero divided by a super duper tiny number gets really, really big. It might be negatively big if it's a negative divided by a positive. It might be positively big if it's a negative divided by a negative. So here we're getting positive infinity because you have a -2 divided by a negative super tiny number. And I should just say more generally, because this comes up a lot, when you have a fraction, if your denominator is really, really large, the overall value of your fraction is very small. Because when you divide 2 by 1,000,000, it's like dividing $2 between 1,000,000 people. Everyone's getting very little. On the other hand, when you divide, or when you have a fraction with a denominator that's very, very small, the fraction value gets very, very large because of what we've just seen here. So here, as we approach 3 from the left-hand side, we're going to see that we have values get larger and larger and larger, like that. You have a vertical asymptote. That's the whole kind of idea with these limits where you have not 0 over 0. You're either going to get infinity or negative infinity, which yes means it does not exist, but also we're saying more when we say infinity. Yeah. There is a horizontal asymptote, which I definitely did draw because I knew it was there. So the way you would find the horizontal asymptote, since we're already there, is you would take the limit as x goes to infinity or negative infinity of 3x minus 11 over x minus 3. The long way of doing this, which you should do at least the first few times, is if you have a rational expression like this, where it's a polynomial divided by another polynomial, you want to divide everything by x to the highest power that is in the denominator. Not the highest power overall, but the highest power that's in the denominator. When they're the same, yeah, that's fine. But occasionally, the power in the numerator will be the highest power, and you want to divide by the highest power that's in the denominator. So here I would divide everything by x. I'm going to get the limit as x goes to infinity of 3x divided by x minus 11 divided by x over x divided by x minus 3 divided by x. You can skip this step, but it's totally allowed, right? I'm allowed to do the same, all right? For a fraction, I'm just dividing the top and bottom by the same thing. That's not changing anything really. I'm essentially multiplying by 1. So I'm multiplying by 1 over x over 1 over x. That's equal to the limit as x goes to infinity of 3 minus 11 over x over 1 minus 3 over x. Now, here's a question I'm going to ask a lot. As x gets infinitely large, what happens to 11 divided by x? Does it get big or does it get small? Small, right? 11 divided by a giant number is super duper tiny. So that's going to be very small. How about 3 divided by something that's getting very, very large? Also small. So whenever you do this, if x is going to infinity, anything that's any constant divided by x or x squared or x to a higher power is going to get smaller and smaller and smaller. So what we're left with here is 3 divided by 1, which is 3. So there would have been a horizontal asymptote here, which I tried to kind of draw, but didn't do a great job of. We'd have a horizontal asymptote at y equals 3. And I should point out that for rational functions, which again are just polynomials divided by polynomials, the left and the right horizontal asymptote are always going to be the same. There are other funky functions where you can get a different horizontal asymptote to the left and to the right, but those are kind of extra complicated. Other questions about this before we do a couple more examples times it. Okay, 15 minutes, all right. Okay, let's look at a couple more examples. Maybe if I can do the paper. So let's look at, yeah, that's a good example. The limit as x approaches 4 from the left of x minus 1 over x squared minus 16. Same idea as before. I'm just plugging in x. So I'm going to get 4 minus 1, which is 3, over 16 minus 16, which is 0. Now, good question. Is that 0 a slightly negative number or a slightly positive number? Slightly negative, because my x value is a little bit less than 4. That's a little bit less than 16. If it helps, and it does help sometimes, we could have factored the bottom as x minus 4 times x plus 4. And then when you plug in a number a little bit smaller than 4, I'm not actually plugging it in, but I'm saying, oh yeah, 4 plus 4 is 8, but a number a little bit smaller than 4 minus 4 is slightly negative, and the negative times the positive is still negative. So then, is my overall sign positive or negative? Negative, because I have a positive divided by a negative, right? If it helps, write that as a plus 3. And then, oh, that's going to be negative infinity. So when you have limits like this, non-zero divided by 0, if they're one-sided, your answer is always going to be either infinity or negative infinity. Technically, your answer is really always going to be that it does not exist. But we should give more information if we can. We should say it's not existing and getting infinitely large, or not existing and getting negative if we are able to.
So if it just as it approaches 4, which is still going to do that?
Good question. So to do the two-sided limit for any one of these, we have to do the one-sided limits first. So if I want to answer the question, what's the limit as x approaches 4? I first have to answer the two previous questions, which are, what are the one-sided limits doing? So I'm going to look at the limit as x approaches 4 from the right of x minus 1 over x squared minus 16. And that's going to give me a 3, but now the bottom is going to be slightly positive, because I have a number a little bit bigger than 4 squared minus 16, which means that limit from the right-hand side is positive infinity. And so then, since the left-hand limit and the right-hand limit aren't going in the same direction, right? One's going up, one's going down, we would say that this limit does not exist. And we wouldn't be able to say anything about the direction overall because they're not both going the same way. And again, graphically, this looks like at positive 4, I have a vertical asymptote. And as x approaches 4 from the right, we're going up. As x approaches 4 from the left, we're going down to negative infinity. There's another vertical asymptote at x equal to negative 4, but I'm not worrying about that right now. I'm just drawing it this way. I suppose we might as well answer the question about the horizontal asymptote here as well. So I wanted to find the horizontal asymptote. To find the horizontal asymptote, you're always just taking the limit as x goes to infinity, or the limit as x goes to negative infinity. And again, for rational functions, they are the same. So let's just look at the limit as x goes to infinity of x minus 1 over x squared minus 16. And now I'm going to divide everything by x squared. I mean, if the limit as x goes to 0 of x over x squared minus 1 over x squared over x squared minus 16 over x squared. It is totally fine to skip this step if you're comfortable doing the simplification without writing all this. So we could skip that step and say, oh, the limit as x goes to 0, x over x squared reduces to 1 over x. 1 over x squared is just 1 over x squared. X squared over x squared is 1, and 16 over x squared is 16 over x squared. And now, 1 over x is going to go to, oh, I wrote something kind of wrong here. What did I write wrong? It's easy to miss. I missed it. I started off with the limit as x goes to infinity, and then I wrote the limit as x goes to 0. There we go. Much better. So now as x goes to infinity, what happens to 1 over x? Goes to 0. 1 over x squared goes to 0. 16 over x squared gets closer and closer to 0. And we're left with 0 minus 0 over 1 minus 0, which is equal to 0 divided by 1, which is equal to 0. Right, how many times does 1 go into 0? Oh, yeah, 0 times. 0 divided by a number is totally fine. It's when you have division by 0 that we have a problem. Something you will probably eventually observe about these horizontal asymptotes is that, let's go back for just 1 second. When you have a rational function where the degree on top and the degree on the bottom are the same, here the degree on top is 1, here the degree on the bottom is 1, the limit or the horizontal asymptote ends up being the quotient or fraction of the leading coefficients. So here you have x to the 1, and x to the 1 is your highest powers, and the leading coefficients are 3 and 1. So your horizontal asymptote was 3 divided by 1, which is 3. On the other hand, when the degree on top is less than the degree on the bottom, your limit as x goes to infinity ends up being 0, which makes a lot of sense because really you can think of this as, oh, the denominator is a higher power of x. It's going to get bigger a lot faster than the numerator will. So eventually, if you let x be, like if x is 1,000, on the top, you're going to have 1,000 minus 1. On the bottom, you're going to have 1,000 squared, which is 1,000,000 minus 16. So essentially, you've got like 1,000 over 1,000,000, which is small. So as x gets bigger and bigger, the bottom is really going to outpace the top. And so the limit's going to be 0. And in general, that's true. If your degree on top is less than your degree on the bottom, the limit's going to be 0, or your horizontal asymptote is going to be 0. Cool. How much time do I got? 7 minutes. All right. Let's do that one. Oh, yeah. So I should give you, one. Let's look at something like, sure, the limit as x approaches, let's do that. 4 of, x cubed plus 1 over 4 minus x squared. So notice I've asked you for the two-sided limit. For these kinds, if you plug it in, you're going to get not 0 over 0. So we know automatically that we have to look at the one-sided limits. We don't have a choice. If you just plug it in and say you get 64 plus 1 over 0, that's 65 over 0. But I don't know if that 0 is positive or negative. I mean, technically, you might be able to say something about the fact that you know it's squared, so you actually do know it's always positive. But we should still show the work. So let's look at the left-hand limit. Now let's look at the right-hand limit, sorry. So as x approaches 4 from the right of x cubed plus 1 over 4 minus x squared, I'm going to get 65 on the top. Okay, now I would encourage you to show this work. 4 minus a number a little bigger than 4 is very, very slightly which way? Negative, slightly negative. But then we're squaring it. Sorry, that was kind of loud. Then we're squaring it. I don't mean that if I'm talking too loud, let me know. Sometimes I kind of yell because my hearing isn't the best. So if you like James, you can quiet it down. I won't take any offense. I'm happy to hear the feedback if I can hear it. So the bottom here, you have a 0 that's slightly negative, but you're squaring it. And when you square something, negative times a negative is positive. Positive times positive is positive. So whenever you square something, it ends up being positive. So what you really have here is a 65 over a very slightly positive number, which is going to give us a positive infinity. On the other side, as x approaches 4 from the left of x cubed plus 1 for 4 minus x squared, you're going to get 65 over a slightly positive number, right? Because 4 minus a number a little smaller than 4 is going to be positive. And then if you square it, it's still positive, which means we're going to get a positive infinity. So personally, what I would say here is that the limit as x approaches 4, I should say the two-sided limit as x approaches 4 of x cubed plus 1 over 4 minus x squared is equal to positive infinity. Graphically, what this means is that both sides of the vertical asymptote are going upwards. So if you were to graph this, or at least graph the part around x equal to 4, you'd have a vertical asymptote, and both the left side and the right side would be going upwards towards infinity as x approaches 4 from either side. I should reiterate, even though I've said that these limits are infinity or negative or whatever, it still means that they all don't exist. Because for a limit to exist, it has to be equal to a real number. And infinity is not a real number. It has to have some nice finite value. All right, we might as well answer we got 3 minutes. We might as well answer the question about horizontal asymptotes here. So let's look at the limit as x goes to infinity of x cubed plus 1 over 4 minus x squared. Yeesh, I don't love that. If it were me, I would multiply at the bottom because I know that I want to divide everything by the highest power of x in the denominator, but it's going to be easier to do that if that bottom is multiplied out or expanded out. So let's write this as the limit as x goes to infinity of x cubed plus 1 over 4 minus x times 4 minus x is going to be 16 minus 8x plus x squared. But I wrote it backwards because I like writing the x squared first. So really x squared minus 8x plus 16. Okay, right? Yeah, that's right. So now we're going to divide everything by x squared. So we're going to get the limit as x goes to infinity. Okay, I'm going to skip a step and just do the division. X cubed divided by x squared is x. 1 divided by x squared is 1 over x squared. X squared divided by x squared is 1. 8x divided by x squared is 8 divided by x. And 16 divided by x squared is exactly what I just said. Okay, so be careful here. Things get a little bit weird. If we let x go to infinity, here's what we're going to get. We're going to get infinity plus 0 over 1 minus 0 plus 0. Right? Because the 1 over x squared goes to 0, the 8 over x goes to 0, the 16 over x goes to 0. And so we get infinity divided by 1, which is, last time I checked, still infinity. So is infinity divided by 2, or infinity divided by 3, or infinity divided by any constant is still going to be infinitely large. So what that means is we don't have a horizontal asymptote. As this function goes to the right, and I know I didn't draw it this way, but as this goes to the right, it's going to go back up like that. And as it goes to the left, well, we got time. We got a minute. So we'll do it real quick here. The nice thing about doing the limit the other direction is it's not really a lot more work. We've already done all the work. I'm just going to change the direction. So we take the limit as x goes to minus infinity of the same expression, x cubed plus 1 over, let's write it as x squared minus 8x plus 16. I'm just going to rewrite it like this. It's the limit as x goes to minus infinity of x plus 1 over x squared over 1 minus 8 over x plus 16 over x squared. I'm not doing the work. I'm just copying what I already wrote. And then, just like last time, that's going to go to 0. That's going to go to 0. That's going to go to 0. But now I'm left with negative infinity divided by 1. So as x goes way to the left, this graph actually goes down like that. And now my graph doesn't look very nice. In fact, it might be worth looking at. Sure. Just so you all can see it. Do I have the time? Not really. But I want you to see it anyway. Sorry. You can, if you need to go, you're welcome to go. I just want you guys to see this real quick. Here's what the graph actually looks like. It was x cubed plus 1. Divided by 4 minus x squared. And so if you zoom out a bit, you can see, oh yeah, you got that vertical asymptote at 4. And then to the right, it goes up and up and up to infinity. And to the left, it goes down, down, down toward negative infinity. So that's what's happening. No horizontal asymptotes here.